I'm going to talk on solving tract-level instances of political districting, and actually this is a joint work with my advisor, Dr. Buchanan, and also Eugene. And yeah, I want to also thank Jamie for his talk. It really helps me to continue talking about districting. And yeah, let me start from a story. It's kind of the first kind of districting model in the OR community that also Jamie addressed that. It's like a non-partisan political redistricting model that was proposed by Hess and his co-authors. And in this paper, they just consider kind of population balance and compactness. And the compactness here is actually moment of inertia, okay? So now I'm going to talk more about the Hess formulation, okay? You can see that it's very similar to the capacitated facility location problem, when we have these kinds of constraints, and then we have xij, and xij is 1 if vertex I is assigned to a vertex j, which represent the center of a district. And constraint 1d, you can see that it's like a population balance constraints that capture the population balance, and pi is here the population, and L and U should be very close, okay, because we want to have a population balance, okay? They cannot be too far from each other. What we considered here in our paper is 1% deviation. And the number of districts is k. The objective function tries to capture actually compactness, okay? It is called moment of inertia, and it tries to minimize the cost of sending people from a vertex to the center, okay? That is why it is kind of calculated by p times distance between I and j squared. But you can see there is no contiguity constants. And then contiguity constants or connectivity constants are considered very challenging in the literature and in the districting problem. And I'm going to talk about contiguity constants mainly in this talk. And also you can see the polytope of Hess that is defined here. So the next question is how people capture the contiguity. I want to talk about a flow-based formulation that was first proposed by Shirabe for districting problem. So consider a very simple grid graph. Suppose that the population on each vertex is 1, and then we want to have 5 districts such that the population in each district is equal to 5. Okay, we want to partition this grid graph to 5 districts such that each of them has exactly 5 people. And then the idea is like, for example, if 6 is assigned to 2, then 2 should be able to send the flow of with a label 2 to vertex 6, okay? And this kind of guarantee the connectivity that we can have in this graph. And this is the main idea. And after imposing those constraints and solving the model, we can have such a nice figure on the rightmost side. And this kind of impose contiguity by flows. So now you can see the Shirabe formulation. So that was the general idea. But here we have a flow variable that is labeled by the origin of sending the flow. And then again, we have Hess formulation, but some flow-based constants are also added to this model. This black constant are added to the Hess formulation. And now this guarantees the connectivity. And then we have the polyhedron of shear formulation. We call it shear, okay? So, but it was proposed by Shirabe. And then we come up with kind of another formulation by disaggregating the flow, okay? Here, the flow of Shirabe has just one label, the label of the origin. What if we want to consider the label of origin and destination, okay? Then we go to a new formulation that we propose as multi-community flow formulation. And you can see that flow has 2 labels here, A and B. B is the origin of sending, is the origin of the district, and A is a vertex in that district, okay? And then again, we have Hess formulation, okay? And these black constraints that impose connectivity. And the polytope of MCF is also denoted by P of MCF here. Okay, so these are the flow-based formulation that I talked about. Now let's talk about the cut formulation, which was first introduced in 2017 by Onart and his co-author. And the idea is like very simple. It is like, for example, if vertex 6 wanna assign to the center, to a district that is centered by vertex 10, then at least one of these vertices in the separator or the cut vertices here, or the 6-10 separator that you can see here, then at least one of them should be selected, okay? And the idea is that, okay, so we said that, okay, if XAB is equal to 1, at least one of these vertices in the set C, which is called the AB separator, should be also selected. And then this is for every A, B, and C, so we have exponentially many constants. Then we have exponentially many constants, then we should talk about separation problem. And we will do that, okay, in the next few slides. And then we have the polytope of cut. So you can see that there is no flow variables, okay? But the size of model based on the number of constants really increased to exponential. And then the next model that we come up with is the L-cut formulation. We found that we really don't need to consider all these red vertices here. We can actually minimalize these red vertices to, for example, here, just one vertex. Why? Because we can use the information of the population that we have. I mean, if I remove vertex A, the node weight distance between 6 and 10 increased to 7. But what is the upper bound for population? It is 5. So it is violated. It means that if I remove vertex 8, then there is no way that 6 and 10 can be in the same district, okay? So the general idea is like minimalizing the set C in the previous model to a new C here that you can see. And then we call it P of L cut. This is the polytope of the formulation. And then we show that the L cut formulation that we propose is the strongest formulation that we can have for such a formulation, that we consider kind of connectivity and population balance and some measures in the objective function that can be compactness. And then we show that the cut formulation is actually equivalent to MCF formulation. MCF is an extended formulation for the cut, and the Shirabe's formulation that is usually used in the literature is the weakest one. And now we should talk about, okay, L cut and cut are strong, but they have exponentially many constants. Okay, now I'm going to talk about the separation. The separation is polynomial if we have integral separation for both models, cut and L cut. And the fractional separation is also doable or easy for cut formulation if we have fractional points, if you want to separate fractional points. But it is NP hard. The fractional separation problem is NP hard for L cut formulation. And then we just gave the models to Groovy to see what happens. And then we found that, oh, it really struggles to, for example, solve the LP relaxation of Hess in the node 0 of the branch and bound for example, Oregon or Oklahoma. So with just this number of vertices or tracts. So we just thought about, okay, not all vertices or land parcels can be the center of districts. Maybe those that are in the marginal parts of the state cannot be the centers, okay? So then we use a Lagrangian technique, reduced cost fixing technique, to fix lots of them. So you can see all the green vertices or land parcels cannot be the center in the optimal solution. Okay, so we can safely fix them in the node 0 of the branch and bound, and then we can just consider the blue centers and start the model with those centers. Then we can see that you can solve them in more reasonable times, and actually we solve them to optimality for 21 states in the tract level. And actually, if we actually relax the time, we found that we can also solve the Indiana in the tract level, which is actually the largest instance that is solved until today. And you can see some maps of our model. They are all connected. We try to keep them compactness, but who knows what compactness is? It's like an eyeball test, but we consider moment of inertia and connectivity is respected, population balance in 1% range is also respected for these maps. They look cool, but we don't have any claim on these maps that they are good or something like that. Okay, so we have no claim on that. And then for conclusion, we could solve 20 states. We could solve cut formulation for 21 states And we could find feasible solution for all states except California. And then we found that COT and LCOT are actually faster than others. And then we found that contiguity is not the bottleneck, okay? This is what usually researchers say, but it is not the case. And for future work, we plan to solve all tract level instances, including Texas and California. And we can also, we plan to consider other compactness measures. Okay, thank you so much.